Hello, everyone, and welcome to this technical session. It will be our last session at SIBGRAPI 2021, Neural Networks and Classifiers. And for this technical session, we are going to have 6 papers from which I'm going to present the videos, and then we're going to have Q&A parts. The first presentation is by Matheus Roder, Enhancing Shallow Neural Networks through Fourier-Based Information Fusion for Stroke Classification.
Hello everyone, I am Matthew and I will present a brief overview of our work in enhancing shallow neural networks through Fourier-based information fusion for stroke classification. First of all, the stroke is characterized by an injury that abruptly strikes the brain issue. It can be classified into ischemic, which is a blockage of a vessel, and hemorrhagic, a rupture of a blood vessel. The first image stands for the two types of the stroke. The first representation is for the hemorrhagic, in which the rupture of the vessel occurs on the left side. On the other hand, the ischemic stands for the blockage of the vessel. On the right side, we have another image that represents 3 CT scans from the brain, in which the first one stands for the healthy brain, the second one for the ischemic stroke, and the third one for the hemorrhagic stroke. Our proposed approach, named multimodal Fourier-based RBM, which is the restricted Boltzmann machines, the shallow neural networks employed, propose to represent information in different domains through the Fourier transformation. The use of information fusion for the training of RBMs can successfully be applied to the problem of stroke detection and classification, since the images can be transformed. The first image stands for an example of 2 inputs in which we have the multimodal RBM based on the Fourier transform. The first RBM receives the original CT scans. Here we have one sample. With Gaussian visible units, we can learn the patterns from the image. The second RBM, learned together with the first one, receives the phase from the same image from the Fourier transform. Both networks learn to detect patterns in the unsupervised manner, and after this procedure, we can fine-tune all the weights of the network with backpropagation. On the right image, we have the same CT image from the brain, in which we can apply the discrete Fourier transform to capture the phase angle from the Fourier transform and the magnitude from the Fourier transform. And these 2 measures or images, new images, are used to feed the new networks, the multi-Fourier-based RBMs, in which the first one, denoted by P, we have the phase input, together with the Gaussian RBM as the first image. The second RBM, multimodal, with PM, we have the phase and magnitude, together with the Gaussian RBM. And the third one, we have the multi-Fourier RBM with the magnitude from the Fourier transform. In this manner, we have 3 multimodal RBM with Fourier-based information with fusion to the Gaussian RBM. The results achieved on the given dataset regarding 2 data splits, which is 50-50 for training and test and 75-25 for training and test, showed us that the Gaussian RBM achieved the best result overall, and the multimodal RBMs achieved also greater results and better than the baselines from the baseline work. For the second split, with more data, we have the better result coming from the multi-Fourier RBM with phase angle, which stands the higher accuracy, and all the models in bold was greater than the baselines CNN1 and CNN2. Thank you all.
Thank you, Mateus.
Thank you.
Yeah, I'm going to ask a question first after we went through the audience. I noticed you have, well, I watched your full presentation, and I noticed, if I'm not wrong, that the actual use of the Fourier, the phase of the Fourier, didn't help much in the final accuracy values. Is that right?
Well, the magnitude doesn't work so good as the phase, and which I think that the phase can carry more information than magnitude, principally mainly by the reason that we have by the real part and the imaginary part from the Fourier transform.
Okay, and another question would be, from my perspective, when I see the images that you show, it seems that it's quite clear what should be the right class. So as a baseline, for example, in some data sets, benchmark data sets, they use as baseline the actual pixels of the images as input to a network, because the image is not that the resolution is not that high, so you can just like flatten the pixels and input this into a neural network, for instance. Did you try this approach as a baseline?
Only the pixels, no. I normalize it with in a Gaussian, normal Gaussian, with 0 mean and 1 unit of variance. But the raw pixels, I do not test.
Yeah, this could be interesting, because then you can see like an actual interesting baseline. In this case, you don't need to use any training for your Boltzmann machine, right? So you just input the pixel directly to a softmax.
Perfect. Thank you.
There is a question here from David. David's bringing questions from the reviewers that he received during the review process. So in order to achieve a more robust conclusion about the uses of RBMs and Fourier transform, the authors could include more experiments with different parameters. What do you think about it?
Well, I actually did more experiments, and in the final paper, I only kept the best ones. So if we look at the parameters, we have, for instance, 2,000 of hidden neurons, and I tested with 3,000 and 1,000, but 2,000 was the best one, and with the original and final configuration of learning rate and momentum.
Okay. Thank you, Mateus.
Thank you.
We can move on to the next one. All right, so now we have the second paper for this session, and I would like to ask the people at our audience at the YouTube to send us the questions right away. You don't have to wait for the video to end, since we have a little bit of delay from the studio to the YouTube channel. So the next paper will be conformal layers, a nonlinear sequential neural network with associative layers. The presenter will be Eduardo Vera Souza.
Hi, this is a small briefing on the work Conformal Layers, a nonlinear sequential neural network with associative layers. I'm Eduardo, and this work was developed by me, Leandro Fernandes, and Cristina Vasconcelos. Convolutional neural networks, or CNNs, are a type of neural network embedded with convolutions to perform feature extraction. Due to the nature of the convolution operator, CNNs are mostly used to find patterns, compress, and transform ND discrete signals. This fact made convolutional neural networks become popular in many areas like astronomy, biology, robotics, and security. The capability to find complex patterns and relations between components of the input signal are strongly related to the depth of the neural network. As the called shallow neural networks are commonly used in some datasets to perform simple inferences, deep neural networks are needed to some datasets to achieve a reasonable accuracy. It would be very interesting if you could mitigate the impact of the number of layers on the inference time, obtaining constant inference time regardless the depth of the convolutional neural network. And that's exactly what we did. By representing the input data and any map of features produced by the network as points encoded as vectors and the conformal model for Euclidean geometry, we were able to represent the most common CNN operations in a conformal embedding of sequential layers of CNNs called conformal layers. By associativity, one sparse matrix and one rank 3 sparse tensor computed after training are sufficient to encode a sequential CNN made up of any number of conformal layers. In this context, associativity refers to the mathematical property of some binary operations. To enable this associativity, we needed a new nonlinear activation function defined in a tensor form. Therefore, we present RESPRO, a nonlinear differentiable activation function that can be represented as a composition of a sparse matrix and a rank 3 sparse tensor. Such sparsity was essential to save memory during the computation of the neural network. Talking about memory usage, we've computed the amount of memory used by our approach during the inference process. By using that composite representation, we were able to run the inference process over 89,000 images using conformal layers with almost the same amount of memory of the approach using conventional CNNs, which could run the inference over only 14,000 images. Besides the memory usage, we also compared the inference time of this approach as we increased the batch size. Since we couldn't run the conventional approach for batches larger than 14,000 images, we've estimated it by using a linear regression. This estimation is depicted by the orange X markers on the plot. The blue plot shows that conformal layers are faster than the conventional approach, even for larger batches. As we showed before, that's the depth impact of the inference time. As we increase the number of layers, we notice a constant inference time for conformal layers. Our main contributions are a new nonlinear and differentiable activation function. The first approach for sequential layers of CNNs, where the linear and nonlinear layers are associative. Accuracy comparison between conventional CNNs against CNNs implemented with conformal layers. Computational performance comparison of conventional CNNs and conformal layers-based CNNs. Thank you. We hope you enjoy our work.
Thank you, Eduardo. I have a question about the baselines that you used. I noticed you use the activation functions that you use were linear or the rectified linear units, right?
Yeah.
However, there are some new functions not that new anymore, like 2017, 2019. There are switch and mesh that were proposed to improve over ReLU functions. So why didn't you use, for example, a mesh function as baseline?
Well, it's mostly due to the complexity of the activation function. Since ReLU is partially linear, it's probably less complex than other approaches like switch, for example, and it leads you to a more interesting comparison when checking the approach of the overall approach, the overall complexity of the approach.
Yeah, I guess what you're trying to achieve is somewhat different from what Mish is trying to achieve. Because in Mish, the idea is to avoid that inflection point at zero. In your case, you're not trying to avoid that, right? You're doing another thing. So one thing that I didn't understand is that constant time. It looks like it doesn't matter how many layers you have, but in my view, it should increase at least linearly, since for inference you have to compute every one of the layers, don't you?
Partially, not necessarily. Since once the train is complete, the entire matrix, the entire tensor that encodes the weights of the neural network are already computed. So regardless of the amount of the depth of the neural network, what we have is the same tensor product. So it doesn't matter about the depth of the neural network. So we always have to do the same operations.
I see. So this is the inference time. That was my bad. Like during inference, right? Not during training.
Yeah.
Okay. Yeah, that makes sense.
The training is still the same, right?
Yeah. I was my mistake. But yeah, thanks for clarifying it.
Yes.
I do have some other comments here from anonymous reviewers. While the computational improvement obtained with conformal layers is clear, the same not happening regarding the capacity of CNNs built with conformal layers. So how does the number of parameters of the capacity or the inductive bias change with conformal layers?
Well, right now we didn't test this kind of stuff, since we don't implement bias right now on the convolution layers. We're trying to figure out how to do this, and that's probably next steps. But about the capacity of prediction and accuracy terms, what we have is what we have a small drawback on capacity right now. That this is a completely new approach, and we're trying to figure out how to improve this feature on the neural network.
Cool. Yeah, I guess still something that's in some sense is still ongoing work, right? You intend to continue this.
Yeah.
And there's another question here about accuracy. I also noticed this. I think it doesn't have to be something that will stop you from looking into, because we know that accuracies are not everything, right? Especially when you consider future data. So one thing that I could suggest as a last comment here would be to investigate the generalization capability of the network. If this how it generalizes, it could be interesting to see, because often, like regular CNNs, if we train those for sufficient epochs, it will reach loss near zero. So it's very hard to measure generalization, because everything on the test set would be like the generalization comes directly from the test set.
It's
so this is an
over
effect
50.
of Yeah. That's not necessarily overfitting, right? Because you can reach loss near zero and not overfit the data.
Mhm.
So maybe you could, yeah, it's yet another thing that I think it's worth studying in your approach.
Nice. Thank you. Thank you for
But
the suggestion.
thanks, Eduardo, for your answers.
Thank you.
We can move on. So our next presentation is a convolutional neural network based mobile application to bedside neonatal pain assessment. The presenter will be Lucas Carlini.
Hello, today I'm going to present our work named the Convolutional Neural Network-Based Mobile Application to Bedside Neonatal Pain Assessment. Our presentation is divided into introduction, materials and methods, results and discussion, and finally, the conclusion. More than 500 painful interventions are carried out during the hospitalization of a neonate in an ICU. Moreover, the correct identification of pain is challenging due to the fact that neonates are not able to verbally communicate pain. In this context, methods based on AI allow the implementation of non-invasive computational frameworks that are specific to the pain phenomena and enable continuous monitoring of the neonate. This paper presents a computational framework based on CNNs to automatically identify the facial expression of pain units, optimizing it to a mobile environment and showing feasibility in real clinical situations. Moreover, we use an explainable AI method to identify facial regions that might be relevant to pain assessment, leading to a better comprehension of the facial expressiveness of a neonate when experiencing pain. Materials and methods can be briefly described in the following steps. Firstly, we collect our data from two face image datasets. Then we apply facial detection algorithm and use the data augmentation technique on those images. Finally, we adapt a convolutional neural network to be used on mobile environment. We use two face image datasets. The ICOPE has 200 images from 26 units, and the UNIFASP has 360 images from 30 units. We applied the state-of-the-art retina face detector in order to extract the face from each image. Then, for each training sample, we applied data augmentation to generate 20 new images. Our classification model is based on the VGG face architecture, originally trained for facial recognition. We applied transfer learning of the original convolutional layers and performed a random search to find the best architecture of fully connected layers in order to maximize the classification accuracy. Our results suggested two new fully connected layers with 512 neurons each, able to classify the facial expression into two classes, pain or no pain, without pain level detection. Using the Android OS and the Android Studio IDE, we developed a mobile application capable of detecting a neonate's face and classifying it as a pain or no pain with low latency and offline. The camera automatically captures a picture, which is then processed by the face detector algorithm. Also, a oval shape helps the user to correctly align the neonate face on the screen. The detected face is inputted in the classification module, which will determine if the facial expression indicates the presence of pain or not. The user will also see the result confidence score and the processing time. Also, our software registers the performance analysis and makes them available for query, containing graphs about the total number of analyses, days, and hours when a specific neonate was assessed as with pain or no pain. The training process was carried out to obtain three classification models, individually using the UNIFASP and ICOPE datasets and with the combination of both datasets. However, they were all tested on both datasets. Our results showed that the model trained with both datasets obtained a better performance with 89% accuracy and was later optimized for mobile inference with similar performance. We believe that these results are suited for neonatal pain assessment since commonly used clinical pain scales achieved similar results. And lastly, we applied the integrated gradients algorithm to verify how much information each pixel of the image adds to the final classification of the model. In general, we observed that the regions of the forehead, nose contour, and nasolabial groove were highlighted, and specifically on pain image, the mouth region with protrusion of the tongue was also highlighted. This work presented a computational framework implemented on mobile environment that uses AI to automatically identify the facial expression of pain in units, showing feasibility in real clinical situations. Moreover, to the best of our knowledge, this is the first work to apply explainable AI techniques in neonatal pain classification, presenting results that agree with pain scales used by neonatologists. As future work, we intend to carry out practical tests at São Paulo Hospital and evaluate more recent CNN's architectures. Thank you.
Thank you, Lucas, for the presentation. I do have a few questions. I read the paper quickly, like just give it a look, and also watch your full presentation. And I noticed two things that you mentioned. One is about explainable methods, but actually, to be quite honest, like I didn't see everything that you are describing. Like for me, it wasn't that clear what was happening during the inference for pain and no pain. And did you use any like or intend to have any expert to take a look at those and see if they make sense with the point of view of the experts?
All the images were captured during painful procedure. So we know that the baby was indeed with pain. I think the ICOP dataset, some specialists classified the image as well, but the process of data collection was similar.
Okay. And the other question would be, I noticed that you have two data sets, right? Basically, do they have a fixed training and testing split?
We performed a holdout validation, but we collected like 10 partitions of the data set.
But because since you are comparing the usage of different sources and combined sources, when you did the comparison, all test sets were the same. Did the test sets were the same, or did you change the test set during those different evaluations?
Yeah, we changed it. For each we collected 20% of each data set and combined it, and then we tested on it.
Okay, so yeah, that could be a limitation, because then I would mention the second thing. There's a term that I think it's people use it in a wrong way, because it's a nice word, but generalization. When you talk about generalization, the actual concept is the difference between the loss function, the value of the loss that you obtain in training and in testing. Did you measure this difference between training and testing loss values to check if generalization was really improving?
Yeah. The main point of testing in both data sets is that the UNIFASP was collected here in Brazil, and the ICOP was collected in the US. So the babies are different. We can think of the ethnicity of each baby. So in terms of generalization, we believe that testing of both data sets is best, is the better.
Yeah, because this includes external validation. Yeah, I see. Okay, I'm going to see if there's any question here. Yeah, well, the
One
anonymous
of the
anonymous
questions,
reviewer here says
yeah,
that there is yeah, it's related to my question. So
yeah,
if you use it, it was not clear that both data sets were trained together and the test set was also a mix of those two data sets, or if you just like did it cross data set, train with one and test with the other.
yeah. Like I said in the presentation, it was three models that we tested. Uh, the first one was only trained with the Unifast dataset. The second one just with the ICO, and the last one both datasets. However, all the three models were tested in both datasets.
Yeah, yeah. Of course, when you train with both data sets, the results should improve. Okay, yeah, yeah. I think it was
Yeah,
clear from the presentation.
nice.
All right, thank you. I think we don't have more time for questions now. Thanks, Lucas. Right, so we can move on to our next paper for the session, which is one class classifiers for novelties detection in electrical submersible pumps. This is going to be presented by Lucas Mello and Gabriel Batista.
Hello everyone, my name is Gabriel Soares Batista, the first author of this paper with the title One Class Classifiers for Novelties Detection in Electrical Submersible Pumps. This research has done at the Federal University of Espírito Santo in Brazil. In this study, we approached the detection of anomalies and fault novelties in electrical submersible pumps, ESP, widely used in the oil and gas industry. The subject of study is a high interest in the industry due to the scarcity of fault examples to train classification systems. Faults in submersible electric pumps generate an enormous cost for companies in the oil and gas sector, since the cost of stopping production to change the equipment is excessive, which make it necessary to identify problems before implementation. An ESP is an equipment composed of electrical motors, pumps, and seals. Accelerometers are attached at the strategic positions of an ESP for collecting vibration signals. Once the sensor attached to the ESP is tested in a sub-table laboratory and under certain frequency and flow operation conditions, each sensor measures the acceleration of vibration at a set point in the ESP. However, signals in the frequency domain are still difficult to diagnose by traditional machine learning methods due to the high number of points per signal and due to the complexity of the relationship between these points. Due to this difficult, a set of features was started with the help of specialists. In this article, two algorithms for anomaly detection, one class SVM and isolation force, are successfully used as effective methods for detection fault novelties in this type of equipment. One-class classification methods are a viable option for anomaly detection since they require only one target class, typically the normal class. These methods are able to detect if new incoming data belongs to the normal class or not, without requiring any training examples from the abnormal class. For comparison purposes, a random forest trained in a conventional binary classification manner is tested and achieved a macro F measure of 0.95, being considered as an upper bound classifier. It is interesting to note that one class classifier also deals with a binary problem. The problem setup is inherently different from the binary classifier used as upper bound. The upper bound requires samples from all classes for training, whereas the one class uses only the normal class. A traditional tenfold stratified cross-validation is used to evaluate the upper bound random forest and the one class solution. The entire dataset was divided in tenfolds of almost equal size and class distribution. For the upper bound random forest, the different fault signals are converted to abnormal examples and the binary classifier is evaluated. The same configuration is used for one-class classifiers, but fault signals, abnormal examples, are removed at training time. Empirical evaluation showed that both one-class classifiers had a satisfactory performance in solving the problem, obtaining a macro F measure of approximately 0.86. Even though both one-class classifiers have similar overall performances, the ability of the isolation force to detect more anomalies than the one-class SVM makes the former method more appropriate for your application. The results show a good performance in both evaluated one-class classifiers. Results came close to random forest performs a binary classification task using additional data not available to the one-class classifiers. The results obtained show that both one-class classifiers behave similarly. They have a great power of generalization in this type of problem, so that the proposed solutions can have practical applications in the classification of problems in electrical submersible pumps.
All right. Thanks, Gabriel, for the presentation. Now we're going to talk with Lucas, which is a co-author. So, Lucas, my first question would be, well, I saw that you treated this problem by looking at the models. So I didn't see in your presentation much emphasis on the data itself, the features used for this type of approach. So, can you mention what would be the important features for this? For example, random forest would be with random forest you could output this type of information.
Yes, I can. The features actually are the most important thing in why these models achieved a good result. One of the features is, for example, just the peak amplitude of the uh, rotation frequency of the signal after transforming from the time domain to the frequency domain. Other feature is uh, some features are very complex. I'm trying to remember the simple ones. One feature captures behavior in the beginning of the signal. What it captures is how the amplitudes decreases from the 3 hertz to 20 hertz. How this is
Okay.
calculated is a little more complex because it's complex because a specialist told us how to compute this. This is uh, a
Yeah.
thing that
I-
has in mind.
Okay. Yeah, because I think sometimes we focus too much on the algorithms and the methods, and then um, in the end, what matters is the features that are used during the process. Also, you mentioned like in the title there's a novelties in plural, but actually when you run the models, it's just like either a binary classification or one class approach, which just detects abnormal from normal behavior, right? So in one class approach, you just model what is a normal behavior, and then anything that goes outside this, it's considered abnormal or outside uh, the training set. So in this scenario, what are if you know it, what are the novelties that you're looking for, or is it just like an outlier detection, something that's it's just to capture what is outside normality?
Our initial intention is to detect a new fault that we are currently not knowing. That was our new intention. That that's why we write novelties to detect new fault types that we are not knowing. But as you said, our work, our paper is based on a one class classification, normal, abnormal. That's just this.
Okay, so in there is a question here that comes from your reviews that you've received. Um, the The author, well, they mention that the authors should discuss the influence of noise and outliers on the coefficients a and b of the exponential regression. So is there any noise and outliers that, because then you may mistake novelties from, well, the opposite, right? Noise or outliers as novelty.
The reviewer is talking about the feature that uses exponential regression, right? There is something we have done in this feature to avoid noise. That's not said on the paper. It's right, not said in the paper. We don't get uh, all the points of the signal to make this exponential regression. We get some of them so that uh, the exponential regression don't do something uh, out of our initial objective. Well, it's a good idea to write this on the paper. It's
Yeah.
I agree.
Yeah, just a last burning question from me. I think it's related to the last one that was posted here, to the practical usage of this type of method. We know that this may change. There's possibly drift in this type of scenario with respect to the features. So and those methods, though, they don't consider time in their modeling. So do you think the in practice is it something that could be applicable, on a day-to-day basis, or does the operators should like train one model per day in order to be able to capture this drifts?
I cannot say if uh, in the future, in a future data, different data will be good or not. We are depending very much on the specialist features. If the specialist features are generic, generic for any type of fault, the methods, the models will work successfully on a drift model, on a future data.
Mhm.
We are trying in future work, uh, as I said in future work, the paper, we are trying deep learning models. So we are not dependent, very depending on a specialist for feature engineering.
Okay. Thanks, Lucas. Thanks for the discussion. We can move on
Thanks.
to the next paper, which is GCOD, a generic coupled out of distribution detector for robust classification. That is going to be presented by Rogério Ferreira de Moraes.
Hello everyone, my name is Rogério Ferreira de Moraes. This work entitled GCOD, a generic couple of distribution detector for robust classification, was developed for me, Rafael Evangelista, Leandro Fernandes, and Luiz Marte. Problems of classification of data of distribution old samples. One the big problem with old data is that some classifiers misclassify them with a high degree of confidence. And in some scenarios, such involve medical diagnosis, it can be a serious problem. Based on this problem, we propose an O detector. And how this will work? As an illustration, suppose our classifier knows an airplane image. Then the classifier must give an output of probability represent pink color give by softmax function. And our classifier will take this as input and must return no OD. On the other hand, if it is unknown class of classifier, such as a car, the detector must have an output indicate OD. Most jobs that detect OOD use the least two datasets, one for training and one for test. Doing this way can generate bias, and as a way to avoid this, we also propose a new methodology for training. GCOD, the proposed OOD detector. We can say that GCOD is a binary CNN. This vector is ordered the size k, where k is the number of classes. In each of these layers, we have k one-dimensional convolution running in parallel, with a kernel value equal to 1. The purpose of having convolution layer running in parallel is to make them behave like fully connected layer running in parallel. At the end of each layer, we have a normalization and a ReLU activation function. The kernel value is equal to 1. And because unlike image, we take kernel greater than 1 because it makes sense to analyze the neighborhoods of pixel. As the class have no neighborhood relation, it makes no sense for a kernel greater than 1. The number n represents the number of layers. There is a hyperparameter. Each fully connected layer is followed by a dropout. The number m is the number of fully connected layers, which is a hyperparameter. The output is binary given by a sigmoid function. Now we will only give a brief introduction on how to use the Voronoi diagram and graph coloring so that we can remove some class from the dataset that will be used as OOD class. The Voronoi diagram is used to know what the closest neighbors are. Note that in figure, if we take 0 neighbor must keep some information. So when remove class, we will be careful not remove neighbor classes. When coloring graph, we must paint with verse so that its neighbor do not have the same color. Therefore, know that the verse that the same color are not necessary neighbor, as we can with the blue and black color on the left side. We can take a number of the class, but just for didactic purposes, let's restrict it just 7 classes. And let's assume that the graph coloring result is what is given by the figure. We can pull the set of class at the same time as long as they are the same color, and with that we got a way to remove a class without destroying information contained in dataset. Contribution. You present the GCOD, a single sample OD detection approach to be coupled with any training discriminate classifier. We present a new methodology to train OD detection approach using Voronoi diagram and graph coloring. Thank you.
Thank you, Rogério, for your presentation. Well, I noticed you use graph coloring as a way of dealing with this type of problem. And we know that a graphing coloring algorithm is time complexity is number of squared to the number of vertices. So how does it impact the results in this case? Is it too complex computationally? Sorry, you have to unmute.
Okay. No, in relative complexity, this complex is easy. No complexity because it's necessary the class this output, the classify, softmax, the probability softmax, and the a coupler and the no uh,
Yeah,
no
because
complex no
well,
complex
well, it could be because you tested on 10 classes, right? But if you try to run the same thing on, let's say, ImageNet, which has 1,000 classes, so I guess it grows with the number of classes, right? So
okay,
the
okay, but uh, uh, we testing for 10 classes in relation 100 classes or more classes. The difficult uh, uh, construction diagram of Voronoi because it stay more
yeah,
in relation, we know no experiment.
okay,
I don't know
okay.
response.
So that just another question here for the last one. If you can answer, is it's a comment from the reviewer. You use the one class SVM to handle the OOD problem. So would it be many one class classifiers? So if you have any, do you have to train multiple um, of them or just one?
Sorry, I don't understand. Multiple. Sorry.
Yes. How? So you use an SVM to train to handle the OOD problem, right?
Yes, SVM. Yes.
Yeah. So would there was many one class classifiers or just one? Does it require just one classifier or multiple?
Yeah, but we use SVM because the classes stay was together, uh, but was analyzing OD, no OD,
Okay.
binary. Okay,
Okay.
SVM analyze binary. E Node OD together, we observation together because we uh, uh, observation that using SVM because together
Okay.
SVM.
Okay. Thanks, Rogério. So we are ready to move on to the next one. So last but not least, representation learning for image retrieval through 3D CNN and manifold ranking that will be presented by Lucas Barbosa de Almeida.
Good morning, I'm Lucas Barbosa de Almeida from Nesp Rio Claro and I'm going to present the paper Representation Learned for Image Retrieval through 3D CNN and Manifold Ranking. Despite notorious advantages, deep architectures often require a huge amount of data for the training stage, which can lead to the limitation of their use in many situations. To overcome these shortcomings, in this paper we propose a representation learning approach that exploits a rank-based formulation to build more comprehensive and effective representations based on the same amount of data. Our approach is used on an unsupervised image retrieval scenario applied on action recognition datasets. In order to present an overview of our approach, we have the following figure. Firstly, We use a transfer learn formulation based on a 2D CNN trained in another large-scale dataset. The 2D CNN are used to rank the images from the analyzed dataset, composing the set of ranked lists tau2. Step 1. The computed rankings define the sequence of images that are used as input to a 3D CNN, so that, instead of considering the temporal information, the similarity relation of the neighborhoods of the image is used. The 2D CNN is also trained by transfer learn, and the features tracked are used to compute other set of rankings, denoted tau3. In the last step, both rankings defined by 2D and 3D CNN are fused by manifold learning algorithm in order to compute the final retrieval results. Step 3. Manifold learning methods tend to explore more global similarity relationships. The computed similarity measure considers the entire dataset and not just pairwise comparisons, considerably increasing the retrieval efficiency. Briefly describing the manifold learning method used, the LHRR uses a hypergraph model to explore the similarity information and transform it into ranking models. And secondly, we have the BFS tree, which, using a tree structure, the method explores the similarity information encoded in the ranked list reference. The experimental evaluation of this approach was carried out on 3 image datasets described below: Willow Actions, Ecclesia dataset, and Stanford 40 Actions. Our experimental protocol considered different sequence scenarios considering 5, 10, and 15 nearest neighborhoods. The parameter KR defines the size of the neighborhood sequence. As measure of effectiveness, we consider map and precision metrics. For the Willow dataset, it is possible to notice map relative gains of 31.38% compared to the 2D CNN and 80.37% compared to the 3D CNN. For the Ecclesia dataset, occurs map relative gains of 37.47% compared to the 2D CNN and 4.45% compared to the 3D CNN. Finally, for the Stanford 40 actions, it is possible to notice map relative gains of 56.93% compared to the 2D CNN and 30.05% compared to the 3D CNN. As you can see, in our dataset, the scenario considering 5 neighbors obtained by results, so we will use it in the visual analysis performance. In order to enrich the discussion on the proposed approach, we employ dimensionality reduction methods, more specifically, the TS11. For each dataset, the distance obtained from the features of the 2D model is presented, followed by our approach. As you can see in the representations, the approach based on ranking fusion resulted in better separability of classes for all scenarios, resulting in a better recovery efficiency. In this paper, we propose a representation learn approach, aiming to improve the comprehensiveness of representations used to achieve more effective results on image retrieval tasks. In the experimental evaluation, our approach achieved significant effectiveness gains on retrieval tasks conducted on action recognition datasets. In our scenario and datasets, the proposed approach achieved better results in comparison with the 2D and 3D CNN models in isolation. Our results are promising for representation learning, and as future work, we intend to investigate the use of the proposed approach in multimodal scenarios, aiming to fuse information from multiple modalities in unsupervised multimedia retrieval scenarios.
Right, thanks Lucas for a nice presentation.
My pleasure.
So I do have a few questions about it. So one thing that was not clear for me from reading the paper and looking at your presentation as well was how actually did you evaluate it within each data set? So it's a retrieval task that you want to solve, right? So you do have the features that were extracted using different methods. And then afterwards, did you use every image in the data set as query to search all images? How does it exactly work?
Exactly, pretty much it. I took every image as query and evaluated the precision map and P of X precision at X.
So yeah, I think with this method, with its way of evaluating, maybe since you are combining neighbors when you do 3D convolutions using images that are close to each other in the feature space. What you're doing is you're producing features that come not only from that image, but from other images as well. So you're kind of like injecting features from the neighbors to that image itself. So for me, yeah, it's clear that this would help within the data set. But haven't you tried an external evaluation in the sense that, okay, you can train, for example, you train on CIFAR 10, not train, you extract features using CIFAR 10, and then you use those features to for another classifiers, let's say, for another data set, let's say CIFAR 100. Have you tried this?
Actually, we didn't try that, but I will write down and try in a future work because it's an interesting suggestion.
Yeah, because then you because in this sense, in the way that you are doing now, you assume that you always have all images, all queries, all future queries, and
Exactly.
for each image that you add to the data set, let's say I have 1 million images, and I have another one that I want to use as query. In order to enrich the data set and improve the method, you have to compute everything again, right?
Everything again.
Yeah, so it's something that yeah. Anyway, um, okay. Um, okay, so let's see if there's any comments on the. Yeah, no comments here. So yeah, I think that's it. I don't think I have any more. I think this was my only concern. But this, since you acknowledge it, I'm okay with it, right? Yeah, limitations are part of any work. Okay,
Thank you very
Lucas,
much.
thank you very much for your participation here. All right, so I think at the we went through all the papers, and now I would like to thank all the authors for submitting your papers to SIBGRAPI and contributing to the conference, and for being present in the conference and presenting and discussing their papers. So I would like to thank also Davi and Afonso for inviting me for being a chair of this session, and also invite you for the next event, part of the event, which will be the scientific awards and the closing that's going to happen in half an hour. So thank you. Thanks the audience for being here, and yeah, I wish you well. See you.